8:30, so thank you for the rise and shine on our last morning. So I'm excited to introduce Matthew Gombolay. He's at Georgia Tech, and I can tell you some really important information about him. He has a private pilot's license. He has 2 kids. He loves music and tennis, and yesterday he had the gym all to himself, which made him a happy person. So please welcome Matthew.
Thank you for the most personal, wonderful introduction I've ever had. It's a pleasure to be with all of you this morning. Thank you for getting up bright and early after our wonderful evening at the Waterfire event. Today I would like to share with you new computational methods and human factors insights that we are developing to essentially get rid of me, to get rid of the roboticist from human-robot interaction and place robots in the hands of end users so that those robots can learn from and interact with those people for customization and performance improvements in their everyday applications. I used to be at MIT Lincoln Laboratory before I came to Georgia Tech, and there I worked on anti-ship missile defense. Pictured here is the USS Bunker Hill, a guided missile cruiser. And researchers have been attempting to make automated decision support tools to help a tactical action officer to make decisions about how to protect the ship against a raid of anti-ship missiles, how to deploy which countermeasures or interceptor missiles, when, where, and how. It's a challenging optimization problem, and they need decision support. So researchers developed that under the Office of Naval Research. Yet when you go on board the bridge of such a ship, what you'll often find is that where there are buttons to turn on decision support tools or automated systems, you will find tape over it with letters spelling OFF. They literally run these systems in the OFF mode. The engineers did not take the time or have the ability to really understand what the tactical action officers wanted and needed before they just went ahead and tried to develop a system and then forced them to use it and put their lives on the line trusting this system. That's not going to happen. And so what we really need are systems that can adapt to end users, understand their goals, and support them in their mission. Yeah, we don't just see this in the Department of Defense. We see this in autonomous driving, where we set up people to fail. Aviation, the recent 737 MAX crashes are a great example. Autonomous path planning algorithms that still are not adopted by NASA rover planners. And then automated surgery tools that are rejected by surgeons. Time and time again, we see that autonomy fails to live up to its potential because the autonomy researcher fails to understand the human and human-machine interaction. My vision is for democratizing robots so that robots can go ahead and understand the end user for me, a very challenging task. And in my work applying this kind of reasoning to manufacturing for the Boeing 777 fully autonomous upright build project, of course, the Navy's challenging anti-ship missile defense problems, my work with the American Nurse Foundation and others, Julie Shaw at MIT, Neil Shaw at Harvard, trying to develop robotic decision support tools for helping nurses coordinate patient care and labor and delivery, and also with my NASA Early Career Fellowship, trying to extend our reach to the stars. Ultimately, I want my own R2-D2. And what you'll notice missing, we have Luke Skywalker piling around with his R2-D2. Am I there? Well, no, I want to be there because it's fun, right? But like, there's no roboticist there. There's nobody programming the back of R2-D2's head there. R2-D2 can learn from and interact with Luke to become a supportive teammate, not just a puppet. And so in my lab, we're working on 3 thrusts to make this happen. First, we're working to give robots insights into human decision-making, both through computational techniques, such as learning from demonstration, as well as through human subjects experiments. Second, we're trying to give humans insights into what the robot has learned through techniques such as explainable artificial intelligence. And then third, we want to scale up this interaction to be able to see true human-machine teaming. Well, let's start with giving robots insights into human decision-making. I'm going to focus on the computational aspects for my talk today. Typically, when you want to develop a robot to deploy it into the field, what you're going to do is pay a lot of money to hire an army of consultants or roboticists, and they're going to go and interview domain experts, such as fighter pilots. They're going to try to codify that knowledge and engineer the human into a box. They're going to put the fighter pilot in a box. And then they're going to put that box on a UAV and then say we've replicated the fighter pilot. And the goals are aligned, the thinking is going to be the same, we've done our job, and now you can pay us a ton of money. That doesn't work. One of the many problems is that experts can tell you maybe what they're thinking about, but not how. There was a really good study done by Bilal et al. In 2008 that looked at expert chess players and set them up to achieve checkmate in 3 moves. But then they changed one thing about the board so that that 3-move sequence was not possible. And they asked them to find an alternative. In a think aloud exercise, the expert chess players would say, I'm looking at the left of the board, the right of the board, the front of the back. I'm looking everywhere. And if you watch their eyes, though, their eyes are tracing out the same 3-move sequence over and over again. 2 phenomena here. There's a disconnect between what operators or experts think they're doing and what they're actually doing. Second, there's an Einstein effect that we get habituated in a certain way of thinking. We have a hard time breaking out of it. So my perspective is that we shouldn't listen to what people tell us. We should watch what they do and then try to reverse engineer the decision-making process. Mathematically, we do this through learning from demonstration, LFD. So let's take in a Markov decision process without a reward function, and we want to minimize the expectation of some distributions of the states of the world that we experience, and we want to make sure that our robot's policy pi is going to try to match or be able to predict what action the expert would take in each of those states of the world. In my healthcare application, we looked at basically air traffic control operations for the charge nurse or the resource nurse to decide which patients should go to which of 6 different wards and then which of the beds within there, which of the various types of nurses and techs would take care of them, and then how to flow them through the operating room to ensure that you would never be left without enough resources to take care of a crashing patient coming through the door, which I did see myself in the 2 years there. There's a huge burnout problem. And so working with Julie Shaw and others such as Brad Hayes and Jesse Yang, who are now both professors, we developed this robot to be able to support them, to actually learn from expert charge nurses, to be able to support all users in the labor and delivery floor. And I'd be more than happy to discuss some of our findings with you later. We've also worked with Lockheed Martin to develop learning from demonstration algorithms to apply it to aerospace manufacturing for the myriad of tasks that are quite numerous, but so diverse that it's basically not the cost-benefit analysis isn't there to support actually hiring an army of consultants and is selling fixed-point automation. One of the things that I really like to think about is the fact that when we collect demonstrations from humans, humans are not machines. Humans are not optimal. Humans often provide suboptimal demonstrations and adopt heuristics instead, operating under bounded rationality. Heuristics help you make decisions fast, reduce your workload. We learn these heuristics over years of experience and apprenticeship, and these rules of thumb really help us to act near optimally. But that's quite different than the assumptions that learning from demonstration algorithms have. Much LFD work makes strong assumptions about at least operators being at least noisily optimal. There's another vein of research, preference-based reinforcement learning, that might kind of get around this. It does require soliciting an abundance of human preferences over trajectories to rank trajectories from worst to best. And this can be useful, but it's not obvious how you can get humans to necessarily demonstrate varying levels of suboptimality, how you can get humans to agree on what suboptimal is, and if you want to automatically generate these trajectories using something like diversity is all you need in RL, that's a really hard problem to solve. So instead, what we're going to do is try to learn what is more optimal than what the human has given us without asking what is more optimal from the person. To do this, I'm going to introduce the noise-performance relationship, building on some prior work by Daniel Brown, Scott Neekum, and others. Let's look at the reinforcement learning problem and Majoko of the half-cheetah, a cheetah-like robot trying to run in the 2D plane with no noise added to its joints. Let's add a little bit of noise, some uniform noise over its joints to make it jitter a little bit when it runs. Like if you've had too much coffee, it's going to be a little bit harder. And then let's inject more noise and more noise. Eventually, it can't even run. Now, the question is, if we add this noise, we can look at the reward that the environment simulator gives us and then plot this on this XY chart, and we can get a curve that tells us what the relationship is for this problem, the relationship between performance and noise. But for a general problem, we don't necessarily know what this correspondence is. And that's the key. If we can figure this out, then what we can do is have a robot imitate a person, add noise to itself, know how much worse it's getting with increasing amounts of noise, and then we could figure out kind of what negative noise looks like and optimize for that, even though that's not like a physically meaningful thing. So some prior work, Drex worked to kind of exploit this idea, looking at the Loux-Shepard rule for learning this ranking of trajectories with varying amounts of noise. First, they used behavior cloning, which is known to suffer from covariate shift, that if you add noise and you get out of the distribution of states that was induced by the expert demonstrator, you're not necessarily going to be able to predict with high fidelity what the expert would do because you're very far away from that distribution. The second is that the Loux-Shepard rule provides an unhelpful inductive bias that if you take 3 different trajectories and you say that they should be ranked, that if you add different amounts of noise to each, say that the amount of noise added to trajectory 1 is more than T0, and then the amount of noise added to trajectory 2 is the most, you'd expect the reward for T2 to be worse than T1 and then T0. If you go ahead and do the math, what you actually find is that it basically creates a line between the reward for T0 and the reward for T2, so that the reward imputed for T1 is halfway between the reward values you'd estimate for the best and the worst trajectories. Well, what we found is that that relationship wasn't always a line. In that previous case, what we actually found was there's kind of the right half of a sigmoid. And so this relationship is not adaptive to the individual domain, and it's generally not a good fit for the statistics of the additional noise that you get. And we test this across a number of problems: mountain car, the performance on the y-axis, and then the amount of noise across on the x-axis for a number of different RL problems and a number of different RL algorithms, A2C, PPO2, and SAC. What we generally find is that first, when you add the Loux-Shepard rule in the red dashed line, that it does not find a good fit to explain the variance of the green line. But if you do a sigmoid instead, it really well explains the variance. So we're going to exploit this. So our method, self-supervised regression, is going to use adversarial inverse reinforcement learning. So we're going to take a robot policy pi and try to predict what actions to take from the state of the world that we're in, say the degrees, the joint angles that we have. And we have a set of expert demonstrations, and we're going to pass both of those into a discriminator, and the discriminator is going to learn to predict whether the action in that state is coming from an expert or the robot. And the robot, in turn, is going to try to fool the discriminator into thinking that its actions are the ones that the human is taking. So we're going to do this procedure. We'll go ahead and then add increasing amounts of noise to the rollouts of the policy, have the robot go ahead and act out in the world. And now we have this 4-tuple where we have the states of the world, the action the robot's taking, the estimated reward we are getting from the discriminator, and then the amount of noise that we've added. We're going to try to figure out, then plot this on this curve, and fit a sigmoid to it, just logistic regression. And then we can take our discriminator and tell it to go back and now fit to the sigmoid that we learned. So it's acting as a low-pass filter here, And we're forcing our discriminator to act like this sigmoid, given its initial estimates in this bootstrapping procedure. And then that's how we get our reward function. Now, we need to make this a little bit robust. I talked to you about covariate shift from behavior cloning. So we take adversarial inverse reinforcement learning, and to account for this distribution shift, we actually play this little trick in the expectation where we do this importance weighting to handle the fact that you want to care more about what the human was showing you than the synthetic noisy demonstrations that you had, because those are less likely to represent plausible behavior. And so we call this noisy AIRL. And so when we evaluate our method, how well it's able to generate a reward function that has a nice correlation with ground truth, what we find is that our approach, noisy ARL generating our trajectory rollouts and learning the reward function with SSRR, that we're able to get a very nice high correlation over 0.9 in our 3 cases with the ground truth reward, whereas prior work was unable to achieve that. And we see this in this scatter plot where the blue trajectory, the red dot is the single trajectory that we receive from a demonstrator. The blue dots are those that we synthetically created, and the green dots are test cases. And we find that we are able to extrapolate to the test cases very well, whereas prior work, DREX was unable to make that switch from the synthetic trajectories to the test trajectories. Note that this case had a synthetic human demonstrator, a robot using an RL algorithm, but I'll show you a real human demonstration in a moment. So once we had this reward function, can we synthesize a policy against it? Yes. So we can actually take our reward function now and learn to do even better than the demonstrator and outperform prior work in doing so. So this is really exciting. So then I had Rohan Paleja and then Lei-Tian Shin are the 2 authors on this paper that got a Best Paper nomination at Coral in 2020, demonstrate how to hit a topspin strike in ping pong. I love tennis. We're not quite yet at tennis robots, but we can do ping pong, thanks in much part to Jan Peters and many others in his lab. And then we can use AIRL as a baseline to look at the return lateral speed, how fast is it moving down, how fast is it dropping, the vertical speed. That's kind of a proxy for topspin. And then what we estimate the reward is, and then we can run SSRR to learn to outperform the human demonstrator. I think we used 7 demonstrations, and we did this in less than a day. It learned in the real world in less than a day. So of course, we want to get it down to like 5 minutes, but it's really cool that we're able to do this on a real system. But humans kind of exhibit different types of suboptimality. So this is actually worse, exacerbated by how the robot needs to learn, and a correspondence problem, a mismatch between what the human thinks of the human and the human thinks of the robot, and then how the robot actually acts. And Dagger makes this worse because Dagger typically works by saying the robot's going to act in the world, driving its car around, and then the human's going to have to sit in the car and use the steering wheel and try to correct what the robot is doing. And correcting somebody with using a steering wheel, correcting the robot while it's driving its car, that's like a really hard problem. You'd much rather just drive the car yourself and say the robot learned from you. And so we need to kind of challenge this notion. Either we need to not use Dagger as an algorithm, or maybe we can help humans, help the robot overcome this noise in the signal or the suboptimality that humans are providing. And so in some of my students working on this project, Mariah Schrum and Aaron Hedlund, what if we assume that there's a set of calibration tasks where we can use those tasks to kind of identify how humans are personally specific suboptimal in the way that they teach a robot a task? And then we can learn this an error correcting mechanism, and then help people teach robots novel tasks, still using this error correction, the procedure that we learned on a set of calibration tasks. And so we developed this approach, MELD, mutual information-driven meta-learning. So you may think that I'm a fan of Star Wars, and I am until 7, 8, 9. I much prefer Star Trek, so Spock. So we're going to use variational information maximization to learn a person-specific embedding that can describe in some lower dimensional space a way to describe if you are overcorrecting the car driving, undercorrecting it, if you're anticipating a turn or delayed in the turn. And we can characterize that, measure how suboptimal you are, and then actually enable the robot to infer what the optimal feedback would be from you. So building on, that was the Best Paper Award at this HRI in March. Building on that, our ongoing work looks at how robots can actually then not just learn how people are suboptimal, but then teach people to be more optimal. So can robots figure out good feedback for people to improve their teaching so that humans can go ahead and teach robots on a variety of new tasks more optimally than they could before? And so first, can robotic feedback augment teaching skills? So can we move people's embedding within this embedding space of describing suboptimality? Second, can we demonstrate the benefit that feedback is going to actually make you a better teacher? And then, can we recharacterize you without needing the calibration task to do so? Because if people are getting better, their embedding would shift. And we don't want to have to recalibrate every time to get the new embedding. So can we actually predict what your embedding is on the fly? And we've had our first study published in a workshop paper, HRI, showing, yes, we can do this. So as a function of the number of round sets you're working with, the blue line is the robot identifying you and then trying to help you. The yellow line is the robot not trying to help, and the red line is the robot trying to make you worse. I always want to show, are we just getting lucky and that people are just naturally getting better with the task, or can we actually control both directions? So that's my deep dive. We're going to go a little bit faster now for the rest of the talk, but I'd be more than happy to answer questions on this part afterwards. Now that we've given robots insights into characterizing human suboptimality, how humans think, we want to give humans insights into robots. And so in a series of papers that we've developed, first one at AI Stats, we built upon this idea by Suarez and Lesko actually back in the 80s of differentiable decision trees. So instead of having a Boolean function, mu, that describes whether a value, say the robot's policy, whether it has to be Boolean, it's either the robot is, for carpool, say it's to the left of the world or left of center or the right of center, we can actually use fuzzy logic essentially and approximate the Boolean splits with the sigmoid. And now that it's continuous, we can use gradient descent on this and say policy gradients. And I banged my head against this idea for a long time trying to get Q-learning to work with Taylor Killian, and I want to thank him for all of his help on this project as well as a co-author. We figured out policy gradients were much better. We have a nice little proof in our paper to kind of support that decision. We've done a lot since then, now working with Ford for autonomous driving to build, instead of just discrete spaces, we can actually apply this to continuous action spaces as well with a paper that Rohan Paleja is going to present at RSS this summer, where we're actually using differentiable decision trees to produce an exact Boolean tree post-optimization. So we're not just giving you the fuzzy tree, we're giving you the exact Boolean decision tree post-optimization by directly optimizing the interpretable representation itself. And we have this nice Robotarium demo as well. And we're actively working with Ford for some data, some highway driving tasks in Michigan. And I want to convey to you something I find really, really important. So some people will say, let's just take a neural network, do deep RL, and then get a bunch of state action pairs, input-output relationships of this neural network, and train a decision tree. And then that's our explanation. Well, if you do that, for all the problems that behavior cloning has, you're going to get a covariate shift. And the policy is going to be very bad. Because your policy is optimizing for an explanation rather than being optimized to be the policy itself. And so in our work, we say that you actually want to develop the math, the optimization techniques, to directly optimize the policy as your interpretable representation so that you can do very well and have it be the actual thing that you go and control the car or whatever robot that you have. And interpretable reinforcement learning is one of the 10 grand challenges posed by Rudin that we've been making a number of contributions towards. But is explanation actually useful? A lot of people have been doing work in explainable AI, but it's actually subjectively and objectively help. Yes, with an asterisk. So we developed a study that was published at NeurIPS last year. First author was Rohan Paleja. And we looked at, can a human-robot team, say in Minecraft, trying to build a house with a fence and a little bench, can they work together to collect resources and then perform this collaborative building task? And we looked at whether XAI, the robot giving a decision tree representation of its behavior and what it thinks the human is doing, the theory of mind decision tree, can it enhance situational awareness, Micah Inslee's levels of perception, comprehension, and projection into the future of what the team will be doing? And then how is that improvement in team performance potentially stratified by experience and the type of explanation that we give? No explanation, full decision tree, or just this is what I'm doing. If you have people watch the human-robot team, and you use a SAGAT, so Situational Awareness Global Assessment Technique, what you find is that, yes, across levels 2 and levels 3, so comprehension and projection of the team, situational awareness is enhanced by giving people a decision tree representation of the robot's policy. But does it improve performance? That's a little trickier. So we find is that humans subjectively will tell you they want the explanation across a number of metrics. And we find that it improves situational awareness, particularly in this offline setting of you watching or having time to think about what the robot and human are doing. But during the mission, we think information overload can occur and actually degrade the performance. We find that particularly for experts, it's actually better for them to just use their own mental model of what a teammate should be and just go forth and execute the task with the robot instead of being distracted with this explanation. Novices can still benefit, or at least the harm is reduced for novices. We think that because potentially they don't really have a good mental model of what a team should be or what a teammate should be, and so explanations could help there. So we say is you want full XAI before to help build a shared mental model, and then online just use simple updates of what you're doing. So lastly, I want to scale to human-machine teaming and how humans, heterogeneous teams of humans and robots can work together at scale and have the robots learn to do the coordination. So let's return to this anti-ship missile defense problem. It's actually way worse because you're not just going to have a cruiser hanging out by itself. It's going to be a part of a fleet. And if you are in a challenging environment, actually at war, well, that's a really challenging computational problem, not to mention a horrific one from the perspective of cost of life. And it's really up to this person, the man or woman sitting in the back of an E2, having to make decisions as a mission commander, and having known some of them, they're very impressive individuals, and it's an incredibly difficult problem. So the problem that they're solving is multi-agent reinforcement learning, a multi-agent coordination problem. And we're going to describe this first simply as a simple temporal network, where we would have nodes describing events that have to happen, say robots in factories. A robot has to start drilling a hole and then finish drilling a hole, and then we can have time bounds, say 6 to 10 minutes for how long the task can or should occur. And we can describe that with the edges between our event nodes. And then we can build this to a graph and say we have 3 tasks with durations 5, 4, and 3 minutes. We can have deadline constraints that task 1 has to finish within 7 minutes of starting. That's emblematic of, say, taking composite material out of refrigerator and trying to build an aircraft with it. Once it warms up enough, it's not workable. And then we can also have weight constraints. One task has to come before another with a 2-minute wait. Say if you want to apply a coat of paint to your house, you got to wait for a while, unfortunately, hope it doesn't rain, and then you will later come and apply a second coat of paint. This is our problem for robotics because first, you have the disjunctive temporal problem. So a robot can only do one thing at a time. So now we have to add in these disjunctive edges and then solve an NP-hard optimization problem to figure out the optimal ordering of which edges we're going to pick. Does task 1 come before or after task 3, et cetera? It gets worse because we're going to now have a team of robots, potentially with heterogeneous capabilities, and now we have to decide which robots are going to do which tasks and the order that it's going to be done. So we've been using in my lab graph neural networks. We started working on this about 3 years ago with student Jiewin Wang. We just had a recent AMOS tutorial that I would encourage you to check out. We look at neural message passing over our simple temporal networks, where essentially our nodes are going to send information about their feature representations, the nature of their task or their temporal event, along edges, also multiplying that with convolving that with some information, also about the edge characteristics, and then those messages are aggregated, potentially with attention, to then produce a new feature representation of each node at the next level. Pictorially, we can think of this as our simple temporal network, with here our graph neural network convolutional operations with attention, and we're going to have our convolutional operators where we have both node features, H in the blue, and then edge features in the pink. And then we can have an attention mechanism to help incorporate that information. And then we can perform those convolutions and develop hierarchical representations of our graphs, compress that into a graph embedding, and then do RL on top of it. We don't typically do RL for most of these problems, so we cast it as an RL problem, because most problems and NP-hard optimization problems, most candidate solutions are going to be infeasible. So everything just has an infinitely bad reward. What can you do with that? So we typically like to do imitation learning, We can get an exact solver, Gurobi or Cplex, to solve those problems, give us examples of small problems, train our neural network weights, and then scale that up to large problems, keeping our learned representation. And so we will first try to train a Q function to predict the efficacy of our actions according to the state action pairs from our expert. And then we will actually use a counterfactual loss to then say any other action that the expert didn't take should have a worse Q value. And that helps us to kind of self-supervise and structure our learning problem. What we find is that we can train our graph neural networks for different objective functions without a lot of tuning and be able to do what I want, democratize robot learning. So now that I have a single learning system that can hopefully learn to whatever application-specific objective function that you have. Of course, there's no free lunch theorems, and I don't mean to claim that we've solved scheduling, but I am very excited and passionate about this work and its power for learning helpful representations for coordination problems. We've applied this to predictive maintenance for aerospace manufacturing, showing that we could save potentially billions of dollars with the representations that we're learning to predict to preemptively repair aircraft, working with Lockheed Martin. We've also applied this to decentralized POM DPs, where agents have different capabilities and need to learn to not only coordinate, but communicate. Because some agents maybe can see in the world, some agents can't. Those agents that can't maybe are ground robots that need to put out fires, and then you have UAVs above to provide some detection and tracking of the wildfire, and they need to learn to talk to each other to communicate that information. And in our recent AMOS paper, we've shown that we can actually compress the amount of information needed for these agents to communicate down to like 16 bits and still outperform previous state-of-the-art methods for multi-agent reinforcement learning. Through this talk, I've shared work that we are doing to first enable robots to understand humans through learning from demonstration. Second, giving humans insights into robot decision-making through XAI. And third, how we can scale this up to human-machine teaming with heterogeneous teams through graph neural networks. And hopefully, one day, we will actually have this vision of our very own robot to support us in our everyday lives. We're working on this. Sonia Chernova is leading our effort at the AI Caring Institute at Georgia Tech, partnering with CMU and others to help support people in the home as they age. I'd like to thank all of my wonderful students in the lab. I am hiring, so please do reach out to me if you're looking for a postdoc or a PhD student position. I also want to somewhat embarrass my postdoc, Nakul Gopalan. I didn't ask him before for permission to do this. He is going to be an assistant professor at Arizona State University in the fall. I would encourage you to reach out to him because I can imagine that he will be hiring. And you should also come see his RSS talk on whether humans can even teach robots through task and motion planning abstractions. The answer is really no, that humans have to be taught to do this. And so he has some really interesting work there. I'd like to thank my sponsors and be happy to take any questions.
We have time for several questions.
Hi. In case of explicit performance, in problems where explicit performance is possible, the ranking of trajectories or learning from trajectories is easy. But where performance cannot be specified or you have to optimize for future unseen situations, how do you deal with that problem?
When it's hard, so is the question when it's hard to define what is optimal, how do you go about optimizing for it?
And also, second part of that problem is future optimality, future uncertainty. Yeah.
Like if optimality might change in the future,
Yeah.
how do you account for that?
Yeah, because you don't have the simulated trajectories or for human performance on that.
You don't have the simulated trajectories. Yeah, so I think that's an interesting question, and I don't think I'm going to be able to give you a clear answer. I think that it is so hard. It's basically impossible today to get a team of people together and agree about what optimal is. We tried with the nurses, and then that was a non-starter. There's like guidelines. You can go to the American Nurses Association, get the guidelines of what is optimal for running a floor. And there's a push to evidence-based medicine, but it's really hard to get two doctors to agree. They'll be like, no, my way is better. So then let alone, how am I going to predict in 10 years from now, like what is the field of medicine going to look like and what is optimality going to look there? What is the patient going to want in 10 years? Like palliative care didn't even used to be a residency training program, and now it is, because we realize that that's actually really important. So with most of the sponsors that I work with, I basically say that whatever we're delivering today, when you actually go and use it, like in a year from now, by the time Lockheed Martin or whoever develops the product, it's going to be worthless. You have to keep updating it to work with people and have people be the facilitator of new demonstrations or new ideas of what is optimal and what their goals are, because that is a moving target that is very difficult to predict.
Okay, thank you.
Yeah, thanks for the question.
Hey, great talk. So I was curious, when learning from demonstration, learning from humans and that type of thing, and I think in general for RL, we optimize for reward. I mean, this is something we've been talking about a lot, and typically a single solution that optimizes for that reward is fine for many problems at hand. But for something like ping pong, for instance, there isn't a single policy that will make you win a match. You want some diversity so that you're not always repeating the same tactics, because your opponent will then be able to learn from that. And so this notion of diversity, I think from learning from preferences and that type of thing, tend to have mode picking behavior as opposed to mode covering. When you have a possible diversity of optimal or near-optimal solutions. And I wonder if that's something you look at, or if it's just too hard a problem, or how you deal with this type of situation.
Yeah, I love this as an athlete and recreational tennis player. Although I wish Rafael Nadal is still a year older than me. I have hope. So we have two papers on learning from heterogeneous demonstration. One at HRI a couple years ago, Zach Leitian and Chen, a multi-style reward distillation, where we showed ping pong that you could actually learn different styles of hitting, but we haven't gotten to like styles, like strategic styles yet. It's a really cool problem, and it is important because you have to fit to exploit the weakness of your opponent. And then the second one, we have a NeurOps paper doing that with differentiable decision trees to try to explain the diversity that we've learned in policies.
Thanks.
Yeah, thanks.
Hey there. I think near the end you had a slide talking about how you're able to reduce communication between these robots. Or
Yes.
the amount of communication. Thinking back to kind of Jacob's talk about that bee dance, or these agents developing novel communication tactics, do you see your robots, which have a very different approach to doing human-AI interaction, developing any of those, or just any interesting, unexpected things you observed in that communication?